planet, which means based on satellite data, we are taking measurements of the ocean, in the atmosphere, over the land, and as well in the cryosphere. We are doing this with a fleet of satellite data. We have 3 screens, building world-class Earth observation system developed with European and global partners to address scientific and social challenges. We have the science stream. These are our Earth explorers. The latest one, number 7, biomass, was launched half a year ago. I will come later to that one. We are doing since the late 70s meteorological satellites for EUMETSAT, and in the middle you see the Copernicus stream, what we are building with the European Commission, operational satellites to monitor our environment. So, Copernicus system is composed of the Sentinel family. You see 6 of them, and I would like to point you specifically towards Sentinel-1 and Sentinel-2. Sentinel-1 a radar mission, Sentinel-2 an optical mission, and Sentinel-3 coarser resolution mission. These 3 are missions which are very useful with respect to forest monitoring. But we are developing these series as well further. The evolution of this Copernicus segment includes 6 new missions, from CO2 over land surface temperature, hyperspectral, longer wave radar, and to cryosphere missions. There specifically, ROSE-L, the L-band radar, will be relevant for forestry. As a CHIME, the hyperspectral, related to species recognition within forests, and LSTM related to forestry health. But we are as well evolving our current satellites to the next generation with enhanced observations. Now, how does it look like? What can we do with those type of satellites? This is an image of Rondônia in Brazil from 1989, taken by the American Landsat. 30 years later, with Sentinel-2, you see how fast Rondônia was deforested, and another couple of years later, 3 years later, you see even more deforestation. Another product what you can get out of Sentinel-2 data is tree cover density. You see here an example over Mozambique. Tree cover density provides distinction between open and closed canopies. That's the reason why I choose as well Mozambique, because there we are more in the dry forest area with larger gaps in between. And you can distinguish then the percentage of the tree cover, which then with the changes of tree cover gives as well indication on forest and the forest biomass. Another tool that is based on radar is a tree cover disturbance monitoring tool, and that gives you information where disturbances in the forest was happening. You see here the color coding according to the timeline. In 2018, sorry. Once again, no. I think it stopped, or yeah, okay. Let's get back to the okay. Blue in 2018, a lighter blue 2019, 20, then the greenish one, 21, 22. And here you see how the development of forest disturbances over time. I used here an area in Laos. It is the expansion of agricultural fields in this area, and which shows how much the area was deforested to the benefit of agriculture. Going back to Mozambique, going back to Africa, to look at evergreen and deciduous forests, and here as well the distinction between the disturbances over time. Here you see a close-up how so the green one was in 2018, the dark blue one in 2021, and the other ones accordingly. And now we're getting to a TCDM radar in Gabon. And here you see the development of roads within the tropical forest, how they were developed over time, and as well then in the vicinity of the roads, the logging activities. Here, a close-up of the area to the top right with its disturbances. And now I'm moving to a completely different topic, biomass. Biomass from space. Within our climate change initiative, we are doing essential climate variables, and one of this is the biomass project. Based on Sentinel-1 and JAXA-ALOS data, we are estimating biomass in 2007, 2010, and annually from 2015 onwards. 2023 is currently under production. This provides data over more than a decade, which are consistent and could be used to estimate change. The change on a global level, change on a continental level, and down towards country level, but not what some people would like to see on field level. But we have as well, as I said before, we have launched 6 months ago the biomass mission. It's is the first P-band star, interferometric polarimetric star, to observe forest height and biomass. Why a P-band? P-band is a long wavelength and is going through the canopy. Like that, we can see more over the overall structure of the forest, and with different techniques we will reveal the biomass, the height, and so on. Now coming to first images of biomass, that is the Amazon, what you see in the middle. As water, it is a specular reflection, and this artificial color scheme makes it pop out then in blue. The green one is volumetric scattering from the forest, and you see as well the red ones at the borders where you see a double bounce, which is characteristic for radar measurements. This part of the Amazon is a little bit further to the west of Belém. Another example is further to the south of Belém. That is a large area in a large mangrove zone. And I was told by Brazilians it's very beautiful to go there. And here, from out the P-band, you see the structure within the mangrove zone. But let's go back to the Congo Basin. That is one of the first images of biomass over the Congo. You see less disturbances. You see smaller rivers inside, but as well the structure of river basins and how the biomass around is can be estimated. But it's not all about forestry. It's not all about satellite. We need the information from the ground, And I would like to make your attention towards GEO-trees, which is a high accuracy ground data collection for satellite-derived biomass mapping. Uh, we are trying to secure 200 plots in the tropical zone where biomass has the biggest uncertainty related to the measurements. Another one related to forestry is the Global Forest Observation Initiative, an initiative to better track forests for climate action. That is an informal cooperation with key activities related to guidance development, R&D, capacity building, and data coordination. And that gives country a possibility to get support when they're setting up national forest information systems. For me, the take-home message is long-term data availability is secured, data policy is full, free, and open data access from our Copernicus, and but we need as well the on-ground reference data, which are essential to unplug the wealth of the satellite data. We are in a data-rich period with clear uncertainty levels and consistency over time. IT capabilities like cloud computing, AI, analysis, and analytics. Let's get into the next level of forest monitoring. And now, let me introduce you to Poliana Bispo. She is professor at the University of Manchester, and she is doing an amazing job in coordinating activities with indigenous people here in the Amazon, which could be as well an example of further south-to-south cooperation in the future. So, come on, Poliana, let's go and rock the show.
Thank you very much. Woo! Okay. Okay, wait. Okay. It'll be difficult to compete. No, I'm gonna talk. It's just wait for 2 minutes for them to stop for 2 minutes. Very good, very good. I need to put in the mold. How can I just go? All right. Yeah. So, like this. Okay, cool. No, don't go away. They went away. They went away. Okay, I can continue, right? All right. So I will start then. Thank you for being here. Okay, so yes, my name is Poliana. I'm senior lecturer in physical geography at University of Manchester, and I'm also a co-lead of the Land and Sources research team in Mary Manchester Environmental Institute. And I would like to present to you today a work that we're doing called Amazonian Biotech Quilombo. And basically the idea is to bridge breeding traditional knowledge and technology to address primarily biodiversity gaps in the Amazon, but we also adding this to biomass estimation of primary forests in the Amazon at the moment using the biomass SAR data set. So here's just a slide showing from a work from Mauricio Santoro, from ISA CCI, showing how complex and how difficult it is to measure accurately tropical forests, biomass in tropical forests, because the forest is very complex, very heterogeneous, and very stratified. So as you can see in this map, for example, on up you have the graph in the right side where you have the standard deviation of this biomass map. What you can see is that the standard deviation here representing the uncertainty is higher in the tropics, in the latitudes that we have the tropics. This is expected because, of course, it's much more complex than the other type of forest in the world. So it's still something to be done, that ESA is doing a lot of work to improve these uncertainties at the moment. And our work, Biotech Quilombo, we also want to tackle and support in this improving measurements of biomass and changes over time. But let me talk about the project. So the project is part of the initiative called Amazonia Plus 10. The idea, this is a consortium between different funding research agencies from Brazil, especially in the states of the Amazon, but you have also other states. That's why it's Amazonia Plus 10, because the 10 states of the Amazon plus the other states of Brazil. And at the moment, we also have involvement in this consortium of UK, Germany, and French Guiana, and Switzerland. So this call for expeditions inspiring this map, where you have, for example, the areas in blue is a probability map. The areas in blue represent the areas where we have lack or low quantity of biodiversity quantified based in the literature. So the idea is to go to these areas, the remote areas, and try to map biodiversity there. So, and another thing that is important to mention about the Amazonia Plus 10 is that they want that the protagonism be from the researchers in the Amazon. So the general coordination is a coordinator from Amazon. And you need to work also with the local communities. And the local communities that we chose was the Quilombola communities. So Quilombolas communities, they are descendants of the slaves in Brazil that they run away from that period to very remote areas, especially in the forest. So they create settlements in the forest, and today they are also still living in these areas, preserving their culture, religion, and ways to deal with the environment. And this is the partners that we have involved in the project. We are 60 scientists, not 40 anymore. We're 60 scientists and 10 Quilombola leaders. And we have 2 universities from Europe, Manchester and Zurich, and the other are universities and institutes from the Amazon and Unesp in São Paulo. So those are the coordinators, including my brother that works with insects, Pythagoras there, and our postdocs and project managers, James and Fernando as well. So just a quick overview. So we have 9 work packages in the project, but the first one, we summarize this in 3 objectives, main objectives. The first one to do the diagnosis of some areas that I'm going to show the map soon for you. So diagnosis of 3 different areas, Quilombola areas in the Amazon, and we're going to map biodiversity of aquatic insects, avifauna, mammals, and trees. And everything trying to link traditional knowledge and technology as well. The second objective is try to do a framework, basically a blender, where we can bring together the different knowledge systems, the scientific occidental knowledge with the ancestral knowledge. Okay, so we're going to use remote sensing, eDNA, and then DNA barcoding based in Quilombolas communities. And the last one, the third one, is a small pilot that we're going to do at the end. Once we have all the data collected, we'll try to automatize this framework with participatory, a community participatory based to try to use artificial intelligence and put them together using, of course, another databases as well to get more data sets and make this friendly, like this interface, once we have all the framework, the interface friendly for the monitoring of biodiversity and forest structure be done in place by the communities. This is the dream, of course, but a long way to go. And another thing that we're going to do, thinking about the biomass side, is try to use our sites together with field plots of other colleagues to help with understand the calibration validation of the biomass SAR. So, sorry, it's in Portuguese, that's a bit there, but basically those are the areas that we're gonna map. We're supposed to go in October this year, but due to some logistical inter-universities problems, UK and Brazil, we postponed and we were going February. So the first area is Marajó, this area here. The second is Oriximiná, Baixo Rio Branco. The third one, the fourth one is Tambor. So we're going all of them, starting in February this year. We're going to do a small expeditions for these areas. And basically, what we're going to do is just to give an overview of the amount of data that we're going to collect. Thinking about the traditional way to collect data sets, we're going to do mist nets for birds. We're going to go to people that are working with insects, fish, and algae. They go to the igarapés, we call igarapés, that is the small lakes in the Amazon, to collect the data set, forest inventories, and so on and so forth. And with the technology, we're going to use environmental DNA. We're going to we do experiment mapping monkeys and birds with thermal drone, and forest with TLS, terrestrial laser scanner, LiDAR drone, and maybe LiDAR, airborne LiDAR as well. And the idea is to characterize these areas using, extrapolate using multi-sensor approach at the end. So I'm almost finishing, so thinking about the biomass SAR and Biotech Quilombo, the objective of our Biomass Quilombo Amazon is try to analyze forest biomass across the Biotech Quilombo project sites, combining field plots, drone LiDAR, and terrestrial laser scanner. Okay, so the study contest, they are, because we're taking a gradient from slightly degraded forest, and primary forest. So let's try to get this gradient to understand how the sensor behave. This range of conditions provide opportunities to compare structural and biomass dynamics across different disturbances gradients, because we are trying to map biomass and also add some information that we have already from disturbances and check this over time, how this works. Future directions is to looking ahead, is to understand the impact of disturbance in the biomass dynamics, biodiversity and biomass interaction, how we can deal and understand this better, and temporal trajectories, monitoring biomass and biodiversity dynamics. So if you are interested in more information about the project, so one important thing, this is the logo of the project. So the logo was, the project was created together with the Quilombola leaders. They helped out. And this is the logo of the project that also was developed together with leaders. So the idea is to use the tools, so the tools that they use is this tool to mash. I don't know the name in English, I forgot. But, and then we add DNA and the satellites at the bottom. And merging knowledge for conservation is a saying um, of Nego Bispo, that is a Quilombola philosopher that used these terms for tell the interaction between territory, nature, and the ways of life that they have. Thank you. And sorry, and I forgot to mention that this is something that we can apply as well in Congo Basin. Okay, so in Congo Basin or any other country as well. Okay, thank you.